My name is Holly Chiang, and today I'll be presenting Dynamic Multi-Clock Management for Embedded Systems. Cheap microcontrollers have made a variety of sensing applications possible. However, many sensors are wireless and have their deployment lifetimes determined by their energy efficiency. To save energy, modern microcontrollers provide multiple clock sources. For instance, the Stanford oil has 7 different clock sources that can be used to drive the system clock. The clocks are ordered from slowest to fastest, and you can see that slower clocks use less current, or power, while faster clocks use less energy per clock tick. This work will show how we can use this to further improve the energy efficiency of wireless sensors. Our system, Power Clocks, is an energy-efficient kernel subsystem that dynamically chooses a clock in response to computation and I/O requests. Fast clocks are used for computation, and slow clocks are used for I/O. This is different from dynamic voltage and frequency scaling, DVFS. In DVFS systems, a slower clock typically lowers the voltage and so reduces the energy per clock tick. In low-power microcontrollers, a faster clock consumes less energy per clock tick. We will show that using power clocks, a sensing application can consume 27% less energy than the best static clock, and within 4% of the optimal hand-tuned clock policy. Similar energy savings can be achieved even when a system runs multiple independent applications. So why is it that in the table I showed, slower clocks use less power while faster clocks use less energy per clock tick? Well, on CMOS chips, power can be divided into dynamic and static power. Dynamic power is dissipated each time a signal toggles and scales linearly with clock frequency. On the other hand, static power is caused by current leaking through power transistors and is independent of clock frequency. The combination of dynamic and static power means that slower clocks are low power. They use less dynamic power and therefore less power at any given moment of time. This makes them energy efficient for fixed time operations, such as I/O. Faster clocks, on the other hand, are low energy. Static power is amortized over more clock ticks, so the energy per clock tick cost is lower. This makes them energy efficient for operations that complete faster when a faster clock is used, such as compute. Our energy efficient clock management strategy works like this. When there are I/O operations, the kernel uses the lowest power clock that meets I/O requirements. When there are compute operations, the kernel uses a low energy clock. When there are both I/O and compute operations, we use the lowest power clock that meets I/O requirements. This trades performance for energy efficiency. The compute operations take longer, but much of the static power cost is free since it would have to be spent anyways because of I/O. If compute is still ongoing when the I/O operation is complete, then the low energy clock can be used. We want to build a system that dynamically selects the most energy efficient clock depending on ongoing compute or I/O operations. However, there are several challenges. Many peripherals require specific clocks or clock frequencies. For instance, a peripheral may require an oscillator instead of a RC clock for higher accuracy, or it may require a minimum clock frequency in order to transmit data at its desired rate. To address this challenge, peripherals should have some way to precisely specify their clock requirements. Some peripherals are also vulnerable to jitter and can produce incorrect results should a clock change occur in the middle of their operation. For instance, if the clock were to change in the middle of a UART transmission, the receiver may sample the wrong bits. To ensure operation correctness, peripherals should have the option to prevent clock changes from occurring while they have ongoing operations. However, this introduces new problems. No jitter peripherals can starve other peripherals waiting for a clock change. Fortunately, energy-limited applications rarely keep operations that require the clock perpetually active. Our proposed dynamic clock management system is called Power Clocks. Power Clocks imposes a split-phase API between a clock manager and clock clients. Each peripheral driver implements a clock client interface and registers itself with the clock manager during initialization. Each client informs the manager of its clock requirements through functions such as set min frequency, set max frequency, set clock list, and no jitter. Before performing any operations that require a clock, the client must request a compatible clock from the clock manager. The clock manager is a centralized component that dynamically chooses the most energy-efficient clock, subject to the clock constraints of peripherals with active or waiting operations. When the active clock is compatible with all of a client's requirements, Clock Manager issues a callback to the client, signaling that it can begin its operation. The Clock Manager does not immediately change the clock upon a client's request, as that can result in a suboptimal clock choice. For instance, if a no-jitter client requests a clock with a minimum frequency of 1 MHz, and the Clock Manager changes to a 1 MHz clock, then a client that requests a 4 MHz clock immediately after would have to wait until the first client finishes its operation before it can begin operation. To avoid this, the clock is not changed until all operations are yielded, signaling that they have submitted their clock requests. Another aspect to take into consideration is that computation is usually either really short, such as in between two I/O operations, or really long, such as FFT, encryption, etc. Changing clocks takes time and energy, so we want to avoid changing the clock for very short computations, for which more energy will be spent changing the clock than saved by using an optimal clock. As a result, for compute operations, power clocks changes to the low energy clock only once an application has spent longer than a heuristic time quanta on computation. To show how the API works, let's step through an example using the ADC. During initialization, the clock client registers itself with the clock manager. Later on, the application requests samples at a specific clock frequency. Considering the limits of its clock divider, the ADC ClockClient calculates the minimum and maximum clock frequencies with which it can achieve that desired frequency and reports the clock requirements to the clock manager. Next, it makes a clock request. The clock manager changes the clock once the application yields and then informs the ADC and other active clock clients that the clock has changed and they can update their clock-dependent values. It then informs the ADC ClockClient that the current clock meets its clock requirements, allowing the ADC to begin taking samples. Once the ADC has finished sampling, it releases its clock requirements and informs the application of its results. The application then begins calculating the FFT based on the ADC results. After compute lasts longer than a time quanta, the clock manager changes to the low energy clock. After the application finishes compute, the application yields. The clock manager does not change the clock since the low energy clock is already in use. PowerClocks is implemented in Talk OS. Talk is an embedded OS written in Rust. It allows multiple concurrent applications to run on a single microcontroller. PowerClocks is implemented for both the MX and TNC 3.6 development boards. Both have Cortex-M4 MCUs with up to 7 different system clocks. The MCUs are from different manufacturers and so have their own implementation peculiarities. For instance, the K66 requires clock changes to follow the paths of a clock state diagram. This slide shows that only a small amount of code is required for a driver to implement ClockClient. The main change is splitting a clock-dependent operation into a make-clock request portion and a clock request granted callback portion. We now evaluate PowerClocks. Unless stated otherwise, evaluation is done on the MX development board. We first evaluate it on a typical sensor application. This application takes 4,000 ADC samples, calculates the FFT, and transmits data over the radio. PowerClocks uses RC fast forward for the ADC samples, RC ADM as a low-energy compute clock, RC fast forward while communicating with the radio, and RC sys while waiting for a GPIO interrupt from the radio. Let's compare PowerClock's energy consumption to that of static clocks. We see that using a low-energy 48 MHz static clock, the application spends most of its energy sampling the ADC, then quickly computes the FFT and sends data over radio. On the other hand, when using a low power 4 MHz static clock, the application spends around the same amount of time, but almost half the energy sampling the ADC. However, it then spends most of its time and energy calculating the FFT before sending data over radio. Lastly, Power Clocks achieves the best of both static choices. It uses the 4 MHz clock for taking ADC samples, switches to a fast 40 MHz clock for calculating the FFT, then uses both a 4 MHz and 113 kHz clock for the radio. Overall, Power Clocks consumes 27% less energy than the best static clock choice and is within 4% of the optimal kernel hand-tuned policy. Power Clocks performs worse than the hand-tuned policies as it waits a 10 millisecond time quanta before changing to the low energy clock for compute, and it uses the 113 kHz RC-Sys, which is extremely inefficient for any form of compute, including peripheral setup, instead of using the 1 MHz RC1M while waiting for the radio operation to complete. This is because Power Clocks cannot know ahead of time how long the radio operation will take, so it uses the lowest power clock while pulling GPIO. Next, we compare how Power Clocks performs on a GPIO I2C flash application. The application first waits for a GPIO interrupt. This is an I/O-bound operation for which Power Clocks uses the lowest power clock, RC-Sys. Next, it takes accelerometer readings over I2C. This is again an I/O-bound operation, though the low power clock for this operation is RC-fast-4M. Computing the magnitude is a quick operation that takes less than a time quanta, so the clock is not changed to the low energy clock. Writing the sensor reading to flash is an I/O-bound operation and uses a low power clock of RC1M. Dynamically changing the clock provides great energy efficiency gains when waiting for the GPIO interrupt takes a significant amount of time. All dynamic policies therefore perform within 1% of each other and consume 55% less energy than the best static clock choice over a 300 millisecond period. Now we show that Power Clocks also works in the case of multiple applications. Here we overlap the ADC-FFT-radio and GPIO I2C flash applications. When the applications execute sequentially, Power Clocks uses 25% less energy than the best static clock. When they execute concurrently, Power Clocks uses 28% less energy than the best static clock. As you may have noticed, there is no hand-tuned policy, as dynamically coordinating clock changes across multiple applications is impossible without sharing application state, which would violate application security. We show the CPU cycle overhead of Power Clocks operations. It includes clock manager logic, but not the cost of actually changing the clock, since any dynamic policy has that cost. Some operations require iterating across pending or current requests, so their overhead increases with the number of active clients. If we have 3 active clients, then the most expensive operation is clock change with 1,442 cycles, which if using a 48 MHz clock is 30 microseconds, a tiny overhead compared with an application which may run for hundreds of milliseconds. For memory overhead, we show that adding clock manager and ClockClient logic for 6 main peripherals requires adding a total of 4.4 kilobytes of code, which is only a 3.3% increase in TOC size. Finally, to show that Power Clocks can be general for different MCUs, we implemented Power Clocks on TNC 3.6. We modified the ADC-FFT-radio application to use flash instead of radio, as the K66 MCU does not support radio. Power Clocks consumes 35% less energy than the best static clock choice and is within 10% of the kernel hand-tuned policy. To conclude, we've shown that embedded applications can save energy by dynamically changing the clock in response to application workloads. Our implementation, Power Clocks, dynamically manages the system clock in the kernel to achieve minimize energy use on multi-programmed embedded systems. It has been demonstrated to show significant energy savings for both single and multiple applications, and does so without requiring any application changes, and with minimal CPU cycle and code overheads. It is general enough to work on different MCUs as well. Thank you for listening to this talk.